the stiffness now changes. Now K is equal to EI over L, where I is the what? Second moment of what? Of area. Different. Okay. So why is it different? If you were to calculate stress, now you guys, I think we'll learn this with Dr. Koshi very soon. I mean, okay, no need to learn from Dr. Koshi. Under axial loading, right? If this is X and this is Y, right? Stress Y is equal to what? Anyone under axial loading? Physics stuff. What is it equal to? What is stress in the Y direction equal to under axial loading? It's very simple. It is what? EY over A. When it's under bending, okay, for this case, it's like the structure is inducing a moment. This is at point B, a moment at point B. Okay. So the stress in Y is equal to moment at B multiplied by Y displacement divided by I. I over here is the what? Second moment of area. So from here, under bending, right? The structure is bending. It's not just axial motion. The deflection now, or your stiffness now, rather than E, is your what? Second moment of area. Are we clear? Okay. Now, don't worry if you have not seen this before. Dr. Koshi will teach this, and then I will teach it also. Wrong. Anyone have a long ruler? Ruler? Oh shit, it's not door. What is second moment of area? Where you? No. When it's inertia, it has to go through certain sort of acceleration and motion. For this case, it's under structural loading. Okay, so I use two terms. Later on, I will teach. Okay. Cross-sectional is okay. If I orientate my structure this way, my second moment of area is lower compared to vertically. Repeat again. If I apply a load vertically, okay, the second moment of area in this horizontal manner is what? Lower than in vertical. Okay, so how do I prove that? If I take my finger now, and when I press, what can you see? The ruler there. Right? And the formula for the second moment of area is V times by what? That power of 3 divided by what? 12. Now I orientate the ruler vertically, and now I put my vertical force down. Can you see the ruler bend? Why? Because this is my width, and then this is my depth, power of 3 divided by 12. Now, can someone tell me? Let's say mommy asks you, son, daughter, Can you explain to mommy what is second moment of area? What are you going to say? You guys do the same to mommy? Mommy only had high school physics. And when I tell her that it's done, don't make sense at all. Or even better, your 6-year-old sibling. I have to do that to a judge. So what is the term you're going to use for second moment of area in this context? Yeah. Is the resistance to what? Bending, right? For this case, the resistance to bending is very what? Low. If you turn it vertically, what happens? The resistance to bending is very what? High. Okay. So I over here is equivalent to the resistance to what? Bending. So if you want, this structure over here, right? What if now, right? Like what I showed you guys before. What if now, right? They tell us, hey, come on. What if in this example again, we were told, right? We were told, okay, you have to use the same beam. I want you to increase the what? Right? If we are going to use the same beam now, we're going to increase the what? Actual frequency. What will you do? Length cannot change. Okay, cross-sectional area cannot change. It's like symbolic. You cannot change anything, but you have to improve. What will you do in this structure? You will orientate the beam in this orientation to where? To the other orientation, yes or no? So in this way, it requires higher resistance to bend. So naturally, you will increase your what? Natural frequency. Are we clear? Past few weeks, it's all just math. Okay, it's not good enough. Okay, I want you to think how to apply. How many of you play? No one playing anything now. No one plays sports. No one plays computer games. Play, okay? You have to be play. Oh no, you're, pardon my French, you're not your miserable bastard. Are we clear? They have to have fun. They don't just study. Getting A my course means nothing. Your mental health is more important. And that's where you have to play. How many of you play Lego? Right? I play Lego a lot up to today. When usually what I do when I play Lego is I love to build houses. I start from the bottom and go up to the top. And sometimes the roof don't work out. How many of you had that problem? Right? And then you will say, I'm going to go into custom bricks, and you go to Lego and find them and don't have. I changed my approach. I build the roof first. Then I go down. It always works. Okay? I was so happy. I went to my civil engineering department. I went to a prof that I know very well. I told him about it. He said, Yuji, why are you so excited? In civil engineering, whatever we design, we look at the roof first and we design down here. And we discover by playing. Play! Are we clear? Okay, no play, you become what? Very sad. Okay, play, innovate. Okay, no play, miserable. Right. So that's all we have for mechanical vibration. The next new topic that we're going to go, okay, we're going to talk about. Some of you are glad, I'm glad it's over. But mechanical vibration is not that bad, yes or no? All right, it's fun. Now this part is really bad. Don't worry. Remember, I told you guys, if you were to look into the textbook, right? When you all go to the textbook, what do you see? Mechanical vibration, where do they put it? They put in chapter what? They put in chapter what? Where is it? If you go down here, they put in chapter what? They put in chapter, oh, really, Eugene? Seriously? They put in what? Chapter what? Chapter 22, right? But it's not that bad, is it? Right now, you look at, I mean, I did not teach everything. Okay, I teach enough for you to know what is linear vibration. I like to highlight this. What I've taught you all is just what? Linear vibration. So the thing go up and down, up and down. Okay, I did not teach you go left and right, relative to the mass. Going to left and right is where we have to go into this form. Okay, so remember, we are only good, or you have been introduced. Okay, so you have to be introduced to linear mechanical vibration. Okay, we don't do, I did not touch on to what? Circular. Right, so the next thing that we're going to do is we are going into planar. Okay, kinematics of a rigid body. Okay, don't panic. It's just big words, but when I explain the big words, it means nothing. Okay, it's easy to understand. Okay. So in real life, what we have is we have three axes. Okay. Axes that we could see, axes that we could feel. We have X, Y, and what? Z. When the word planar came in, okay, planar motion, for example. So whatever I teach, and this can be found in chapter 16, okay, the motion is restricted to XY plane, YZ plane, or XZ plane. Okay. So what it means is if I'm going to sketch now over here, this is known as our what plane is this, anyone? XY plane. Okay. If you're not sure, be sure about it now. Okay, it will help you later on. And over here, this is your what? And the last one, okay, I thought I changed color. And the last one, okay. So we don't do like motion in XYZ all at the same time. Okay, why I teach you from here, we don't do that, okay? Okay, or the theory don't support that, okay? So next we are going to focus on rigid or planar or different types of planar, rigid body motion. Now, you all will have this on Avenue to Learn. Okay. So over here, are four types of different motion. And if I were to draw my transformation, right? If I were to draw my transformation, so we know the planar is on which plane, anyone? HY plane. Every dot that you see will have an X and Y coordinate. And Z is constant. We clear? Now, How does this term come in? How does the term rigid body come in? Yes. Yes, the distance between point A, okay, the distance, I'm going to write down here, the distance between point A and point B will not change. Okay, so distance between point A and B will not change. So this is where we assume rigid body. Are we clear? Okay, I'll see you guys tomorrow. Tomorrow we will have demonstration of how gears work. Have you all learned gear system yet? Yes or no? No, yes, maybe. Okay, we'll do gear system tomorrow. I'll see you guys tomorrow, 9:30.